I'm Dr. Roger, and this is differential equations, in particular a first-order homogeneous equation. Homogeneous is 5 syllables, homogeneous, or homogeneous, but 5 syllables, homogeneous. And homogeneous equations are equations in which dy dx can be written as a function of the ratio y over x alone. So in this case, if I multiply by 1 over x over itself, I get dy over dx equals, 1 over x squared over itself, which I'm allowed to do that because anything over itself is 1, equals x squared over x squared plus 3y squared over x squared over 2xy over x squared. And that simplifies to dy dx equals 1 plus 3y over x squared over 2y over x. So the right-hand side is a function of y over x alone. Anytime y prime is a function of y over x alone, we can make this separable through the change of variable y equals vx. You can also write that as y over x equals v. I prefer y equals vx because we also have to replace dy. We can't have dy dx equals some function of v. We want dv dx equals some function of v. But to get there, dy equals x dv plus v dx. The product rule on dy gives us the correct change to our variable v. So, going back to the original equation, dy is x dv plus v dx, and that's over dx, equals x squared plus 3 vx is v squared x squared over 2xy is 2x times vx is 2x squared v. We notice that the numerator has a common factor of x squared. So that's x squared times 1 plus 3v squared over 2x squared v. And on the left I have x dv plus v dx over dx. Do not separate these terms. Do not try to simplify v dx over dx as plain v. Just leave it as is until we simplify the right-hand side. X squared over x squared is 1. So this is x dv plus v dx over dx equals 1 plus 3v squared over 2v. At this point, I cross multiply. We're going to cross multiply and then combine all dv terms on one side, all dx terms on the other. So I have 2vx dv plus 2v squared dx equals 1 plus 3v squared dv. I'm sorry, 1 plus 3v squared dx. Now I want all my dx terms on the right, so I'm going to subtract 2v squared dx from both sides, which on the left leaves me with 2vx dv, and on the right I have 1 plus v squared dx. As I promised before, the change variables y equals vx with dy equals x dv plus v dx made this separable. Now it looks like something we've seen in Calculus 1 or Calculus AB. Dividing through by x to move the x's to the right, and 1 plus v squared to move all the v's to the left. X over x is 1. 1 plus v squared over 1 plus v squared equals 1. So the left-hand side is 2v over 1 plus v squared dv, and the right-hand side is dx over x. I've separated the variables. At this point, I'll integrate both sides and then solve 2v over 1 plus v squared dv equals the integral dx over x, and both these sides are natural logs. So I have natural log 1 plus v squared equals natural log x plus c. I could put plus c on both sides. That's unnecessary because I can subtract whatever c is on the left from both sides, and I'm left with the difference as a different constant on the right. I could put an absolute value around 1 plus v squared. That's not necessary because 1 plus v squared is never negative. Taking both sides as powers of e to the ln 1 plus v squared equals e to the ln x plus c. And I probably don't care about this absolute value on the x either. So 1 plus v squared equals a different constant c times e to the ln x, which is just x. And I'm dropping that absolute value because I'm happier without it. Now what? This is not the solution to my original equation. My original equation was y and x. This has a v, so I have to substitute back in y equals vx, so v equals y over x. 1 plus y over x squared equals cx. 1 plus y squared over x squared equals cx. I can multiply both sides by x squared and get x squared plus y squared equals cx cubed. I could stop here. I could solve for y. In this case, I'll solve for y. Y squared equals cx squared x cubed minus x squared. Square rooting both sides, y equals plus or minus square root cx cubed minus x squared. If you wish, you can pull out the common factor of x squared inside the square root, and y equals plus or minus x root cx minus 1. And we see that this absolute value on x didn't matter because when we pull it out, we've got a plus or minus. This is the solution solved for y. Anytime you have a homogeneous first order equation, it can be made severable with the substitution y equals vx, and if you can then integrate the two sides once you've separated variables, you can solve the differential equation. There will be many other substitutions for a change of variable that will make other non-solvable first order equations solvable. Come back soon for my next video. With math, there's always more.